We're going to go through some different things today, and the biggest one is the lab simulation. I know sometimes these simulations can be kind of goofy, and so I want to make sure that you're in good shape with that. And so I'm going to pull up the simulation. I'm going to share my screen with you. Pull up the simulation here. And what we're going to do, so if you go into the Schoology assignment, there's a link that to open up the paper for it, but then there's a link that brings you right to the simulation, and so you can do that. And so what I'm going to do here is it says go to the simulation. It says upper right hand corner, click no end, window will appear, click oscillate, and click damping to none, and get the rulers out. So we're going to do that. We're going to go up here and go to no end. We have a window. Click to oscillate, and we're going to move the damping to none. We'll do some stuff with damping in a little bit, but for right now, we'll just keep it without any on there. So we have the wave. We're going to put the rulers out here. A couple of things to note. Our frequency is 1.50 hertz here. And I'm going to pause it, and we'll get the wavelength because we're going to need that on the next part. So if we go here, we got a wavelength. If I go from where it crosses right here, I line that up with the 0. It crosses right there at the red dotted line, and then I have a full wave, so both the top part and the bottom part. So I have the wave that comes down here, and then that's one full wavelength crossing at 4.2 centimeters. And so I need to put centimeters into meters in order to make those calculations. And so we're going to look at this. It says use the rulers to measure the wavelength. I just did that. And record the frequency. And so the frequency is 1.50 hertz. And so we need to calculate the period here. So we'll take period equals 1 over frequency. And we'll say 1 divided by 1.50 because that's the frequency. That gives us the period of 0.67 seconds. So in order, the time for one wave to occur is 0.67 seconds. The second thing it asks us to calculate here is the velocity of the wave. Now, remember, we'll measure it in meters. And so we'll calculate it in meters. We measured in centimeters, and so we needed to move that into meters. And so we'll take 1.50 hertz. That stays the same. Then it was 4.2 centimeters. And so we're going to move that into meters by moving the decimal 2 to the left. And so it'll be 0.042 meters. That's what I have right here. And so when we multiply the 1.50 times 0.42, we get 0.063 meters per second for our velocity. Oh, I have that wrong here. Fix that. And we've got that. So then it says to change the frequency to 2.30 hertz and press play. And we'll get that information. So we'll do that. 2.30 hertz. And you can see that wavelength shortens up. We'll go ahead and pause it. And then we can measure what that wavelength is. Again, I'm going to put the 0 right where it crosses the dotted line. And I'll get it where it crosses here. It crosses right between, so I have 2.2, 2.4, 2.6. It's right between the 0.6 and 0.7 or 0.8, so it'll be 0.7. So 2.7 centimeters is our wavelength here. So we can go back here. 1 over frequency gives us the period, and this one is 0.43 seconds for one full cycle here, and then V equals F lambda. And, our frequency is 2.3 hertz. And then the wavelength this time is 2.7 centimeters, so that's 0.027 meters. When we multiply those two together, we get a speed of 0.6062 meters per second. So we can put the period in here, we can put the frequency or the wave speed in here. We're going to do this again. This time our frequency is going to be lower, and we're going to go to 1.20 hertz. So we're going to slide way back here, 1.20 hertz. It's a nice, long, smooth wave. It can be sort of difficult to actually get. There we go. We got it the first time. Last class period, I struggled to get one that actually fit within our distance here. And on this one, we're right at 0.52 meters. So 0.52 meters. So 5.2 centimeters. If I line this up at the 0 where it crosses to start, and I go my whole wavelength here, I cross again at the 0.5 or 5.2 centimeters. And the frequency is 1.20 hertz. So to get the period here, we take 1 over the frequency and we get 0.83 seconds. That's for one wave, takes that long. And then the wave speed, excuse me, we have 1.20 hertz times 0.52 meters, and we get the 0.62 meters per second. So we put that information in here. It says average the velocities from problems 1 through 3. Well, this one was 0.063, 0.062, 0.062. Those will end up averaging at 0.062. 0.062333333 if we want to get really technical. Then it says to use the average velocity that you just calculated to calculate and predict the wavelength would be for 3.0 hertz. And so we're going to take this speed. So wavelength equals V divided by F. So velocity divided by frequency. So we'll take the velocity that we just got, 0.062 meters per second. We'll divide that by a new frequency of 3.00 hertz. And it tells us by that calculation that it should be 2.1 centimeters. So we can take, and I'm going to slide this bar all the way up. The fastest it'll go is a frequency of 3 hertz. We'll go right here and get this wave. And if we measure it out, oops, sorry, put this right here. So if we go 0 here, and go all the way out for one wave, we're just between the 2.0 and 2.2, so 2.1 centimeters. Yay, hooray, it worked out. So then it says to change the damping so that the slide bar is about halfway over. Notice what happens to the wave. Based on your observation, what does damping mean? So I'm going to go ahead and just kind of clear out some things here. And I'm going to slide my damping here to about halfway over. And so before, when we don't have any damping, the wave stays at a regular height all the way out. That wave continues. When we add some damping, it diminishes as it goes away from the source. And so with that damping, it means you're losing energy as the wave travels down the line. If I go to a lot of damping, it barely does anything. It's like, oh, hey. In fact, if you look at the part in the window, there's not really anything that actually makes it there. It loses energy before it gets there. So anytime you regulate, like in general, if you're creating a wave, there's almost always going to be some level of damping because energy isn't perfect in the way that it would travel. But for what we want to do in our measurements, we generally we do it in a perfect situation because it gives us a better ability to measure what we're talking about. So damping just means that you lose energy as it continues to go. Then we can say change the damping back to none and the tension to low. What effect does tension have on the waves? So we're going to put the damping back to none, and this time we're going to move our tension to low. And that is just a very different looking wave than what we had. If we put our tension sort of in the middle, we get right there. If our tension's high, we're right there. Low, it's kind of goofy. And so it ends up, it shortens the wavelength considerably, even though the frequencies stay in the same. So then it says, once you have a good wave on the screen, press pause, measure the wavelength, and use the frequency to calculate the velocity of the wave, show your work. So if we bring our rulers back, and it's kind of goofy to measure because there's so many lines, but I'm going to we'll pick this one here. We'll go from here to here. ends up being right at about 0.7 centimeters. It's sort of between that 6 and 8 there. So it's not even a full centimeter. And when we go back and we calculate it, we have 2.50 hertz. Oh, was I on that? Nope. Let's move it back to here. So I actually have it right. Let me set this up again. There we go. And get it on here. This one will be more clean. There we go. So we measure this right at the 0.7 mark. Is it even? Somewhere in there. And so we can measure that on there, and we can go back to here. We take 2.50 hertz times 0.007 meters, and we ended up with 0.0175 meters per second. So does the lower tension result in faster or slower wave? Well, if we look at our higher tension, our speed was 0.062 meters per second. This one is 0.0175. So it slows it down considerably as we lessen the tension. So it's a slower wave here. Reset the tension to high. In the upper left, click the pulse button. Upper right, click fixed end option. And then the green button to pulse it and talk about what happens to what's going on here. So we're going to go to pulse. I'm going to fixed end. So that just means it's locked in. I'm going to take the rulers away. I'm just going to pulse it one time. I got to switch the tension. Sorry. Otherwise, we're going to sit here forever watching the wave. There we go. So it goes down, comes back. Goes down on one side, comes back on the opposite side. Down on one side, comes back on the opposite side. And the place that the wave is starting is also a fixed point. So goes down, turns around, comes back on the opposite side from whichever side approaches it. It travels back on the opposite side. So we can go back to what we have here. It says click the green button. We did that. Describe what happens to the wave pulse. It travels down and returns on the opposite side of the string. Then it says change the upper right box to a loose end, and we'll do the same thing. So we'll click to a loose end. I'm going to go ahead and restart it. Loose end puts a ring on there, and it allows it to move up and down as it approaches that bar. So when I click a pulse here, it goes down, and it comes back on the same side. Now the fixed end is still there for the place that the wave starts. So when it approaches the fixed end, it flips sides. But on the loose end, it sends it back the same side that it came down on. So it comes down on the bottom, goes back on the bottom, comes up, back, down on the top, back on the top. And it flips when it approaches the fixed end. So when we go back to what we're looking at here and what we're doing, it says, how is it different from the fixed end? It travels down and returns on the same side of the string. All right, keep the wave pulse running. And when the pulse is at the loose end, press the green button to add a second pulse. Describe what happens as the wave pulses cross. It says you might want to step things forward and whatnot. So I'm going to let this go down here. I'm going to push that in there. We get this. So I'm going to go ahead and pause this, and I'm going to step it forward. I can control what's happening here. So when this comes back, these two are on opposite sides, and they're going to meet. When they meet, they briefly cancel each other out and continue on the path that they were going. On this one, they're going to be on the same side. We have both of these on the same side coming toward each other. When they meet here, they build up on top of each other and then continue back in what they were doing. So again, opposite side cancels out just briefly. The wave is still there. They just cancel each other out at that moment. And then it continues along the path. And then once on the same side, they build up, they get higher, and then they continue moving. So if we go and we put that in here, when the pulses are on the same side, they add together when they meet. The pulses are on the opposite side, they cancel out when they meet. And this will actually lead into what we do after break with something called standing waves. In the upper left-hand corner, change to oscillate. Keep on the loose end and set the frequency to 1.54 hertz. Then hit restart and watch the waves interact for a while. Describe what happens to the waves. And then we'll do a fixed end and we'll compare. So we're going to go to oscillate. And so that's just going to keep going. Oh, 1.54. I don't know how I picked that number, but why not? There we go. So we're going to oscillate here and watch what happens as the waves go. They're getting bigger. They're oscillating back on each other. It's called a stand. This is a standing wave. And then they become out of phase and they cancel out for a moment. And then they keep going and they'll get bigger. And then they'll go out of phase and they'll cancel out. And then it keeps repeating itself. Then it says to do this same thing on a fixed end. So we can watch this happen on the fixed end. They get smaller, bigger, they get smaller. Pretty much the only difference, it still cycles through similarly, but the overall cycles of larger and smaller end up being quicker. So for this one, they get larger and smaller as they go. So they add up and then they cancel out, and then they add up and they cancel out. Same thing happens, it just moves through that quicker. And then waveforms add to each other and interfere using the pulse option with either fixed or loose end. Use a combination of pulses to create a unique looking wave. And you can do that on your own. You can get different stuff to get weird looking patterns based on where the wave pulses go. So it's essentially just saying play around with it and see what happens with different things. So what I'm going to do is I'm going to zoom out on this. And if you want to get a screenshot of the top one, please do not just submit my screenshot back to me. That's not what I'm going for. But as a reference to what you're doing, if you miss something, it's there. And then same thing here. I'm going to take a screenshot of that and be able to reference it as needed. The hope is that looking at this simulation, it allows you to figure out just sort of seeing how the waves work and see how different parts work together. So then the next things that we have to look at are some of the practice problems. And I want to actually do the wave drawings first. So let's do this. In the wave drawings, you're going to have several different things you're doing here. So the first part here is so for 1 and 2, you're just counting your wavelength, amplitude, and number of waves. So on this one, the wavelength, if we count here, remember it's the top and the bottom. It's that full cycle that gives you your wave. So how many boxes? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's all the way out to here. It includes both the top part and the bottom part. So the wavelength for this one is 12 boxes. And so what happens a lot of times is people just do half of it, and that's not what we're going for. We're going for the whole thing here. So let's move this here. The amplitude is how high up or how low it goes from the resting line. So our 0 line is here. It goes up 2, goes down 2. So our amplitude is 2. Number of waves. Here we'll have this full wave. We've got 1 and then 2. So we've got 2 waves over here. When it comes to the next one, you're going to do the same thing. There's just one part that's a little bit goofy about it. And it is this. So wavelength, you'll still count out. Go 1, 2, 3, 4, 5, 6, 7 and a half boxes. So the wavelength is 7.5. Your amplitude, it goes up and touches the 2 and then goes down and touches the 2. So it's still an amplitude of 2. Number of waves on this one, it goes 1, 2, 3, and then half of the first half of the wave. So it's an extra fourth. So the number of waves you have on here is actually 3.25. So it's not the full wave here. It's not even half of it because it doesn't go down. This line here is just this part from there to there. So it's just half of that first half. Then it asks you to do some drawing on these waves. It says graph 3 cycles of a wave that has a wavelength of 6 and an amplitude of 4. So the wavelength of 6 means that the top half is 3 and the bottom half is 3. So 3 across, to give you your total of 6. Your amplitude is 4, so it's going up to touch the 4 line and down to touch the negative 4 line. And then you have 3 wave cycles and no more than that. I know there's space to fit another one here. It's not. It's very specifically asking that you only have 3. So we can do the same thing over here. If we have a graph of 2 wave cycles that have a wavelength of 10 and an amplitude of 3. So I'm going to go ahead and add a line in here. My wavelength is 10. I need to change this for sure. Oh, this one in blue. Why not? My full wavelength is 10. That means that half of my wave is 5. And it's going to go up to 3. So 2, 3, 4, 5. Half of my wave, my top part, will go here. It's going to go up to the 3rd line here. And then when I go here to get the second part, it's going to go 5 more. 2, 3, 4, 5. This way I have a full wavelength of 10. Just like that. So I have a wavelength of 10. 1, 2, 3, 4, 5. It crosses at the 5. 6, 7, 8, 9, 10. And then I'm going to have 2 cycles. So I'm going to just copy this, paste it, move it over here. And when you're doing yours, Notability works really well for this. If you are doing it on a computer, I'm doing this in Preview and it's working well just to get the lines and stuff. It's nice that it has that that middle part of the line that you can move. If you're doing this in Notability, you can just use either a stylus or your finger to draw it on your screen. So for each one of these, you'll continue with something like that and you'll get those lines drawn on there as those waves. Lastly, you have your practice problems, and there's a few of them that I want to go through here and talk about. The first one that I want to talk about is number 3. Number 3, you're looking at the concepts of period and frequency. Well, I got to dial into this one real quick. Hold on. Go. There we go. All right, so I'll show you my board in just a second here. And it says, number 3, you have someone who's waving on a parade route, and they have 45 waves each minute, and so that's 60 seconds. And so it's asking you to solve for period and frequency here. And so we did this last week when we looked at this on Thursday, I think. Let me get this up here for you. There we go. So if you're solving for the frequency, you have waves per second. So I'm going to say 45 waves over 60 seconds. So that's going to leave us with a frequency of 0.75 hertz. Then to get the period, we can take 1 over f. And so we'll have 1 over 0.75. And we end up with 1.33 seconds for each wave. So that's what we're looking at on number 3. I just wanted to go through that because it's not quite as clear. The next one I want to talk through is number 6, I think. Yeah, number 6. It says that the speed of sound in water is about 1,500 meters per second. So V equals 1,500 meters per second. A dolphin uses echolocation, sending out a sound and hearing it in return. If the dolphin sends out a sound and hears it 0.8 seconds later, so t equals 0.8 seconds, how far away is the object? And it says use the second equation for this, so speed equals distance over time. Pay attention to it being an echo and think about how sound travels in an echo. So in here, we have to keep in mind that when you have an echo, if this is your sound source and this is what it's bouncing off of, it's going to go out and come back. And so we'll talk about that in a minute with what happens. So the dolphin sends out the sound here, it travels down there, and it travels back. And so if we have speed equals distance over time, speed is our velocity, we're going to solve for distance. So distance equals speed times time. So we have 1,500 meters per second times 0.8 seconds. So 1,500 times 0.8 gives us a distance of 1,200 meters. The thing that's happening here is it goes out and comes back in those 1,200 meters. So it goes half of the way out and then the other half of the way back, that same amount. So if we take 1/2 of 1,200, we end up with 600 meters. So the sound travels 600 meters to the wall. And then from the wall back, it travels that same 600 meters in the opposite direction. So how far away is the surface? It's 600 meters. And that's where that echo piece comes in. All right, if you want to screenshot 3 and 6, you're welcome to do that. Then, let's see, that one. I want to do number 9 and potentially number 10 if we have time. Number 9 says an ocean wave has a frequency of 0.20 hertz. So frequency equals 0.20 hertz. And the wave has a wavelength of 4.5 meters. What is the wave speed? And then how long would it take the wave to travel 1.5 kilometers? So we can do V equals F lambda. So we have our frequency of 0.20 hertz times our wavelength of 4.5 meters. So if we take and do that, 0.2 times 4.5, we get 0.9 meters per second. Then it says, so this is for part A. Part B then says if it travels 1,500 kilometers or 1,500 meters, 1.5 kilometers, how long will it take? We know that 1.5 kilometers equals 1,500 meters. So now we'll use speed equals distance over time. We can rearrange for time. When we do that, we get time equals distance over speed. And instead of saying 1.5 meters is only, about that long. 1,500 meters is 1.5 kilometers. So we'll say 1,500 meters divided by our speed of 0.9 meters per second. So we can take 1,500 divided by 0.9, and we get 1,666.7. Sorry, time equals seconds. So part A and part B here. If you want to screenshot that, go ahead. And then we'll use the last couple moments to do number 10. Number 10 says, this one's a little bit goofy. It says a flag is blowing in the wind. The waves in the flag have a wavelength of 25 centimeters. So we'll switch that right away into 0.25 meters. And the wind is blowing at 3.0 meters per second. So V equals 3.0 meters per second. What is the frequency of the wave through the flag? And so the biggest thing here is making sure that you get from centimeters into meters. Other than that, the calculation is pretty straightforward. So we have V equals F lambda. If we're solving for our frequency, divide by lambda. So frequency equals velocity over wavelength. So we have 3.0 meters per second divided by 0.25 meters. Remember, 25 centimeters has to be brought into meters. So 3 divided by 0.25 gives us a frequency of 12 hertz. So that's for number 10. Any other ones that cause some confusion that you want me to go through? Nope. Okay. All right then. So here's what we need to keep in mind. This week is about wrapping up this bit on waves. You have your stuff that's coming in. I'll get that quiz up so you can take it. And then making sure that you have the things that you need to end the quarter well. And so if you have work to get in, get it in. Everything is still open. Everything, all quizzes are open. The test is open. All practice problems can still be handed in. Your labs, anything you have can be handed in. If you need a plan on what you need to do to pass, just shoot me an email and I'll take a look and tell you exactly what you need to do to make sure that you can get up to passing. And make sure that you keep moving forward. If you are in good shape, then you do not need to come to class on Wednesday. Wednesday is about making sure that people have what they need to get caught up and end well. So if you're in a spot that I don't see you, enjoy your spring break. Everyone kind of gets a bonus spring break this year. We get Friday off, or you get Friday off, and then the Monday and Tuesday after break you get off. So an extra long time. I feel like breaks right now are just so much more needed than they're normally needed, but so much more. So take some time to get yourself in a good spot to end the quarter well, to end the year well, and we'll be in good shape. If you, like I said, if you're in good shape already, you don't need to be here on Wednesday. If you want some extra direction and getting caught up so you can pass, Wednesday is the time for you. So have an awesome day. Enjoy the nice sunshine today, and I'll see you later. Bye-bye.